Earth from orbit. A unique perspective on time. From space, Earth is a breathtaking blue marble, a swirling sphere of life and color. Astronauts describe a profound shift in perspective from this vantage point. It's a humbling experience that underscores Earth's interconnectedness. Space travel also alters our perception of time. In orbit, time behaves differently than on Earth. This is due to Einstein's theory of relativity. Time is a fluid entity influenced by gravity and speed. Imagine time as a flowing river. On Earth it flows at a certain pace. In space it flows faster, far from gravitational influence. Section 2. Einstein's revolution. Time is not absolute. Before Einstein, physicists believed that time was absolute and unchanging, a universal constant that ticked away uniformly throughout the universe. Einstein shattered this notion with his theory of relativity, demonstrating that time is relative, meaning it can be experienced differently depending on factors like gravity and speed. One of the key takeaways from Einstein's theory is that gravity warps time. Imagine a bowling ball placed on a trampoline, causing the fabric of the trampoline to sag. This is a simplified way to visualize how massive objects like planets and stars warp the fabric of space-time, with time being one of the dimensions being warped. The stronger the gravity, the more pronounced the warping effect on time. This means that time slows down in stronger gravitational fields. Don't worry, this effect is incredibly subtle on Earth. Your feet age ever so slightly slower than your head due to the difference in gravity between your head and your feet. However, in extreme gravitational environments like near a black hole, this time dilation effect becomes much more pronounced. Earth's pull. Gravity's influence on time. Here on Earth, we are under the constant influence of gravity. It keeps our feet planted on the ground and dictates our daily lives. But gravity also subtly affects how we experience time. Earth's weak gravity causes minuscule time dilation. Escaping Earth's gravity, time ticks faster. Weaker gravity means faster time flow. This is Einstein's theory of relativity, experimentally verified. Section 4. The speed of time. Orbiting at a different pace. Another factor that influences time is speed. According to Einstein's theory of relativity, the faster you travel through space, the slower time passes for you relative to someone who is stationary. This might sound like something out of a science fiction novel, but it's a real phenomenon that has been experimentally confirmed. Astronauts aboard the International Space Station, for example, are traveling at incredibly high speeds, orbiting Earth at approximately 17,500 miles per hour. At these speeds, time dilation due to speed becomes a factor, although still a very small one. Due to their high speed, astronauts on the ISS age a tiny bit slower than people on Earth. This time difference is incredibly small, on the order of a few milliseconds over the course of a 6-month mission. While this might not have significant practical implications for astronauts in their daily lives, it highlights the fascinating interplay between speed, gravity, and the passage of time. Section 5. Measuring time warps. Atomic clocks and space experiments. Measuring the minuscule time differences predicted by Einstein's theory of relativity requires incredibly precise instruments. Enter atomic clocks, the most accurate timekeeping devices ever created. Atomic clocks are so precise that they would lose less than a second over billions of years. In one famous experiment, scientists sent atomic clocks aboard airplanes flying around the world, while identical clocks remained on the ground. Upon comparing the clocks, the scientists found that the clocks that had flown at high speeds showed a slightly slower passage of time, confirming Einstein's predictions. Similarly, experiments have been conducted with atomic clocks flown aboard spacecraft. These experiments have consistently demonstrated that time passes slightly slower in orbit than it does on Earth, further solidifying Einstein's theory of relativity as a cornerstone of modern physics. Section 6. Time's cosmic dance. A universe of relativity. So, is 1 hour on Earth different from 1 hour in space? The answer, surprisingly, is yes, but only by a tiny fraction of a second. While the time differences due to gravity and speed are incredibly small, they have profound implications for our understanding of the universe. Einstein's theory of relativity has revolutionized our understanding of the cosmos, showing us that time is not a rigid, inflexible framework but rather a fluid entity that is intimately woven together with space, gravity, and motion. As we continue to explore the universe from the depths of black holes to the vast expanse of intergalactic space, Understanding the nuances of time dilation will be crucial for unraveling the mysteries of the cosmos. The universe is a far stranger and more wonderful place than we could have ever imagined, and time, it seems, dances to its own cosmic rhythm.